Roxana Dumitrescu from INSEE Institute Polytechnique de Paris, and she will share with us recent advances on the linear programming approach for mean field game and fast-slow mean field game with common noise. Floor is all yours, Roxana.
Thank you very much, Renyuan and Yufei, for the kind invitation and to accommodate the talk at the quite last minute. So I will talk, I would like to focus my talk on multi-scale mean field games with common noise. So I will present, let's say, a new approach how to tackle multi-scale mean field games, but in the case with common noise, but without solving the mean field game with common noise, which usually brings some difficulties, okay? And I will rely on some results on the linear programming approach for mean field games, and I will also present some new results about this. So I will start with a brief introduction, then I will talk about the LP approach for mean field games of optimal stopping, and then I will talk about the fast-slow mean field games with common noise. I have chosen to talk about optimal stopping because usually it's a bit more difficult to solve than the case with regular control. But what I'm doing here can be adapted to the case of regular control. So, of course, mean field games, I think we all know that they have been introduced like in 2006 by Las Filions using a PD approach. And the main purpose is to use the asymptotic formulation in order to describe large population games in the case of symmetric interactions, and this allows to provide a tractable way of solving mean field games with a large number of players. I'll remind the standard setting in the case of regular control. So for the n players game, so you have each player controls its state process, where I'm here in the case without common noise. So there are the Brownian motions are independent, so you have a drift volatility. The drift and the volatility both depend on the control and on the empirical distribution of the other players. Then each player minimizes cost functional, where the payoff functionals depend on the empirical distribution of the other players, and then we look for the Nash equilibrium. So if we think about the asymptotic formulation, in the case where there is common noise, we expect that the empirical distribution will converge to a deterministic flow of measures. And in this case, how the problem looks like, so you have the representative player. We have a representative player who is interacting with the distribution of the population. So this is the dynamics of the representative player, where again the drift and volatility, in this case, okay, they depend on the control, but also on the distribution, which corresponds to the distribution of the population, mu t, which is here deterministic. Then we fix mu and we solve a standard control problem. And then we say that we have a mean field equilibria if, assuming that, for example, here I have uniqueness of the best response, so of the optimal control, then the law of the controlled process X along the optimal control has to be mu, the mu that I fixed here. Okay, so in this case we have a solution. So the main approaches that we usually have to solve mean field games yes. So the PD approach, which consists in solving a coupled system of partial differential equations, Hamilton, Jacobi, Bellman for the backward. This characterizes the value function of the control problem. This is standard in control theory. And then we have another equation, which is the Fokker-Planck-Kolmogorov equation, which is forward in time and describes the evolution of the distribution of the population. These equations are coupled. Then we have a more recent approach, the probabilistic one, which relies on the theory of forward-backward stochastic differential equations with coefficients which depend on the law of the solution, so of Makin-Vlasov type. And then we have the compactification method, which allows to solve the problem under mild assumptions by relaxing the concept of equilibria. So we have two main approaches. We have the one of the controlled martingale problem approach, which in the midfield game theory has been mainly developed by Daniel Ecker. And then we have the linear programming approach that we have developed in a series of papers. And yeah, I'd like to mention that this is particularly suitable for the case of optimal stopping. So, what is the linear programming formulation? The linear programming is a compactification technique, okay, which is inspired by the works on the LP formulation of stochastic control by Stockbridge, mainly by Stockbridge. They are related to the control martingale problem approach, which has been introduced in standard control theory by Nicole El-Karoui, Monique Jean-Blanc, and Kühne and Nguyen. And as I mentioned, is particularly suitable for the midfield games with optimal stopping, or with absorption, or with singular control, because in this case the flow of measures is irregular in time, which makes the analytic approach more difficult to be used. So which are the advantages? So if we think about the PD approach, we have two objects which characterize the equilibria. So you have the value function and the population distribution. In this case, we work with only one object, which is the population distribution. So instead of iterating back and forth between the value function of the single agent and the population, the distribution of the population, the problem is formulated exclusively in terms of the population measure flow. The condition that the measure flow is the flow of marginal laws of a controlled stochastic process gives a linear constraint on the measure flow. And this simplifies a lot the theoretical analysis of the problem, in particular the proof of the existence of an equilibria, but also the numerical computation, because the controlled martingale approach is nice. The existence proof is also quite simple, but the problem is that the method is quite abstract and you cannot really implement to compute the equilibria numerically. The problem of mixed controls is not a problem with this formulation, because I will talk more about this relation between LP approach and mixed controls. But this is not a problem because we can imagine that in a population with different agents, the agents can naturally use different strategies, okay? And what we can show the equivalence to strong formulation under appropriate assumptions, and also the equivalence to the other notions of midfield game solution. So if we think about the LP formulation of optimal stopping, so this is a standard optimal stopping. Okay, you maximize this criteria over admissible stopping times. And for any stopping time, you can define a flow of subprobability measures. So M2 represents the distribution of X of the process X killed at the stopping time tau, and mu represents the joint distribution of tau X2. And what you do, you can rewrite the criteria in terms of the occupation measures. You take the expectation, and it's very simple to observe this. And then by Ito's formula, you derive you apply Ito's formula, and then you take the expectation and you get the constraint on the measures m tau, mu tau. Okay, so this is basically a Fokker-Planck equation when you have exit of the players. So how the linear programming problem looks like? So you optimize the criteria that we derived over the measures m, mu, which are admissible, and by admissibility we mean those measures m, mu, which satisfy the constraint for all test functions which are C12 bounded with bounded derivatives. Okay, so what is clear clear is that you remember that I took an optimal stopping time, and I have shown that the measures are associated measures are admissible, belong to this set. The question is now this is the minimal set at some point that we can consider which is convex and compact, because the nice properties of this set would be that the set is convex and compact, so we can apply the fixed point theorems. So what we'll basically do is we'll also derive that we have a one-to-one relation between the occupation measures and randomized stopping. So under these conditions, I will not go into all details. We can show that we have existence of an optimum for our problem. So again, what is very important here is the fact that we have the compactness of the set R. And also what we can show is that the value of our LP formulation coincides with the value of standard optimal stopping problem. It is clear that the value of the standard optimal stopping problem will be smaller than the value of the LP problem. This is obvious. But we can show that we have actually equality. For optimal stopping mini-field games, there are some early references by Carbonat, Delarue, and Lecker, Nutz, where they solve some bank-run models, and a paper by Bertucci where he is interested in the PD approach. There are some the recent references on the LP approach. Then there are some papers on supermodular games, mini-field games. And then a paper by Bossama and Talbi where they derive a master equation. For optimal stopping of Makin-Vlasov dynamics, so this is more related to the control of Makin-Vlasov type, there is a paper by Talbi, Touzy, and Jacques. So if with the n player game problem, so we have n agents. These are the SDEs of each agent. I take the simple case where the drift and the volatility do not depend on the distribution of the others, but the problem can be done with additional solved with additional technicalities, but it works. And what we do, so each agent will solve an optimal stopping problem where you can see that F, the running payoff, will depend on the empirical distribution of those players who are still in the game. So you can easily observe that this will be a sub-probability flow of measures because you have this indicator function. Then mu n is the joint empirical distribution of tau k x tau k. And then what we do, we look for Nash equilibrium. How the problem looks at the limit. At the limit, we have the state of the representative agent, then we fix m, t, a flow of sub-probability measures, mu, a probability measure, and we solve this optimal stopping problem, assuming for simplicity that we have uniqueness of the optimal stopping, which is not always the case, of course. We take tau and mu, the associated solution of the previous optimization problem, and if the distribution of x killed at this stopping time tau coincides with mu m, and the joint law of tau x tau coincides with mu, then, so if we have a fixed point in 2 and 3, then we have a solution of our optimal stopping problem. But the problem is that we not necessarily have uniqueness of the best response. You can imagine that you have a stopping problem where you always have a minimal stopping time and a maximal stopping time. So there is a characterization of optimality which says that every stopping time at which the value coincides with the payoff and such that basically you have a super martingale. The increasing process does not increase, so you have a martingale, then this stopping time will be optimal. So in the case when you don't have uniqueness, things become more complicated, and in this case we cannot expect to have an equilibrium in this form. So we prove that we have equilibria in the LP sense. So how the problem looks like. So okay, I introduced the spaces, the space of sub-probability flows for M, the space of probability measures for mu. They are endowed with the weak, the topology of weak convergence. And we define the criteria to optimize in this case. So we fixed M bar mu bar in the F and G. And in red, I have the M mu bar over which I will optimize. And we say that M star mu star is a LP mini-game equilibria if I fix M star mu star in the running cost and the terminal cost, then this will be the best response. Okay, will be will give the maximum value. And this value is called Nash value. So under these assumptions, in particular, the assumption I would like to insist on is the fact that F, F is jointly measurable and continuous in Xm. So under these growth conditions, but here we can take any p larger than 2, what we know is that we have existence of an equilibrium, okay? And the proof is based on Kakutani-Fan-Gliesberg fixed point theorem, precisely because we don't necessarily have uniqueness of the best response. Now, about numerics, because I said that this approach is good also from a numerical perspective. So the algorithm, which is the linear programming fictitious play algorithm, how it works, you start with a fixed point, a starting point which is admissible. Okay, so for example, you take the distribution of the non-kill process of X, this will be admissible. And what you do, you have a number of iterations. At each iteration, you compute the best response, where here in the running cost and determining cost, I have fixed m bar n, mu bar n, the output from the previous iteration, and which is the output of this given iteration will be a convex combination between the last best response, which is mn plus 1, mu n plus 1, and the previous output, m bar n, mu bar n. And we usually take these coefficients. Of course, we could take also other coefficients, but we need some conditions under which you have the convergence. And if you rewrite this, you can write as an average over all best responses from 1 to n. So for this algorithm, what we prove in the case when we assume that, of course, we assume that we have existence of an equilibrium, so we impose the condition under which this result holds true. Then we assume that F satisfies the last three Lyon's monotonicity condition with respect to the measure. And then we also assume that the best response is unique. And in this case, we have, under these two conditions, we have the uniqueness of the equilibrium. And what we show theoretically is the fact that the flow of measures m bar n, mu bar n converge to the unique mean-field game equilibria in the topology, in this product topology, where for the first one we consider the weak topology, and the second one is the topology of the convergence of in measure over this space. So it was we had to think which is the right topology for M, because as I said, the flow is discontinuous with respect to time. Okay, and we can show that we get the convergence in this topology, but also in the stable convergence topology, and this will imply also the weak convergence. Which are the other developments? We consider settings where you have mixed regular control stopping, coefficients depending on the measure, and also common noise, but which is restricted to a finite probability space in discrete time. We have the numerical algorithm, and we have also developed several applications. I will talk now about the fast, slow mean-field games with common noise. So this is a joint work with a postdoc that I'm co-supervising with Peter Tankov. So as you know, mean-field games with common noise usually are much more difficult to solve. So which notion of solutions have been treated in the literature? So we have a stochastic version of the coupled system of HGB Fokker-Planck equation. So here I'm thinking about the case of regular control. In the case of optimal coupling, there was no really result on the PD approach in the case with common noise. And this is, if we compare to the deterministic setting, this is becomes more difficult. Why? Because in this case, the solution lies in this space. Okay, so for each given scenario omega, so if we think about the flow m to omega, we associate a trajectory from 0 to capital T in the space of probability measures. And this space is not well suited to use compactness arguments. And then another object which captures all the information about the equilibria is the master equation, which is an infinite-dimensional nonlinear PDE on the space of probability measures. So some references in the case of regular control, we have some papers by Carmonade de la Rue-Lecker, a very nice paper on the master equation, and a very long paper actually by Cardelaguet de la Rue-Las-Lyons. And then a paper by Dianetti, Ferrari, Fischer, Nendel in the case of supermodular games. And there is also a nice paper of Charles Bertucci and another co-author on Midfield games with common noise, which has some, the model will be a bit close to what we do in the sense that they introduce the common noise through an additional variable, which will enter the drift, but they solve directly the Midfield game of optimal stopping in the case with common noise through the master equation. Thing that we'd like to avoid here, so to try to see if we can avoid. And so this is in the case of regular control, and in the case of optimal stopping. So of course there are the paper, the ones that I mentioned by Nutz, Carmonade de la Rue-Lecker in the case with common noise, but Nutz has a very specific model, and then the model of Carmonade de la Rue is also in the bank run case, quite specific. Then there is a paper by Xiaolu Tan and some co-authors using the Bankel-Carui formulation for the Midfield in the case of in the Midfield setting. But here there are some assumptions about the common noise, the fact that the filtration is countably generated. Okay, so then we have our paper, but here is, as I said, is in discrete time. Okay, and there is the paper by Posama et al. Okay, so in the case of optimal stopping, there are not so many references, and what we try to do is so we consider a Midfield game. We treat both cases, regular control, optimal stopping, but here is only on optimal stopping that I present, where we have time scale separation structure, okay, and which is the objective is to construct an approximation of the Midfield game equilibria with common noise through a Midfield game without common noise. Which is the structure of the problem? The structure is that the common noise in our setting is introduced via an ergodic process. Okay, and which are the main ingredients? So are the averaging principle, which is known for multi-scale control problems, and there are two main approaches which are usually used for this averaging principle, either using Poisson equations or some discretization of the slow process. I will talk a bit more later. And then what we also need, because as I said, I would like to use the Midfield game without common noise to derive a proxy equilibria for the Midfield game with common noise. We would like to use this LP formulation because it's nice in the sense that we can do numerics and so on. But the only issue, let's say, is that the notion as it is not adaptable to multi-scale structure, okay? So we cannot use it directly, but the existence of an equilibrium in the LP sense will be used as a key step. And what we'll do, we'll prove a rigorous connection between the LP formulation and a randomized stopping. So I will present the probabilistic framework. So I have a probability space, omega fp, and we'll have 3 independent Brownian motions. And we consider 2 state variables, x delta and y delta, which evolve on different time scales. And the parameter delta measures the time scale separation. And y delta evolves according to a rescaled ergodic process. Okay, so which are the dynamics? The dynamics, so x represents the slow variable, so it has these dynamics. Wx is the Brown motion which drives x delta. And then we have the ergodic process, y delta, okay, which is driven by the other 2 independent Brown motions, wy and w hat y. And here w hat y will play the role of the common noise. So now the result which is known and of course useful is the fact that under suitable regularity assumptions on the coefficients, the slow part x delta will converge to the solution of this following SDE. Okay, so we have, and here, so if you look back to my system, you see that here I have taken B, which depends on the fast scale. Sigma is independent. I will explain the reasons for which I didn't include the dependence of sigma on Y. So the reason will be the following, is that here what we know is that if I take this SDE, okay, where the drift is a drift averaged, the average new averaged coefficient B hat, which is averaged with respect to the unique invariant measure of the transition semigroup of the process Y, okay. So what we'll know that we'll have the convergence of x delta towards x bar. So this is a strong convergence, and the rate of convergence is delta power 1 over 2. So in the case, so that's why I took the sigma, which is independent on y, because if we have sigma which depends on y, in this case we do not have strong convergence, but we have rather weak convergence. Okay, so here are some assumptions, but this is not the only set of assumptions that one can consider. So in particular, okay, we have the some assumptions to have existence and uniqueness of the strong solution of the slow variable, and then we have the conditions, the first one, and also this one, so the first two, which ensure the existence of a unique invariant measure. We take the case where we have the less regularity possible with respect to time for the slow variable. Okay, so these assumptions are in a paper by Michael Rockner, who worked quite a lot on multi-scale SDEs, also of Makin-Vlasov type. And now I will present, which is the notion of two-scale epsilon mean-field game equilibria with strict stopping. So here I give the definition in the case we have strict stopping. So the equilibria can be represented in terms of a stopping time with respect to the initial filtration. So we say that tau m mu is a two-scale epsilon equilibria if for all stopping time, which is a stopping time with respect to the big filtration, so the filtration generated by Wx, Wy, and W hat y, we have this. So this is a standard, let's say, definition of an epsilon equilibria. So what one can notice here is that you see that the pair of functions depend on x, on the slow variable, the fast variable. Then we have the measure with respect to x and y, the killed processes x, y. So we have this condition, and then we have the fixed point, if you want, is m epsilon delta is an adapted process, which, and mu is a random measure, which satisfy the conditions. Okay, so this gives us the fixed point. Which is the mean-field game equilibria for the limit problem, which will be a deterministic mean-field game, deterministic in the sense that we solve this in the case when there is no common noise. So here, of course, as it is with common noise, we have the conditional distribution with respect to the common noise. So here, how the problem looks like. So we say that tau mu is an effective mean-field game equilibria. So in the literature on SDEs, multi-scale systems of SDEs, we use the notion of effective SDE. So here we use the notion of effective mean-field game equilibria. So it is an effective mean-field game equilibria if for all tau prime, which is a stopping time with respect to the small filtration generated only by Wx, okay, we have this optimality condition, okay, for tau, where here the payoff f1 bar is the payoff, it's f1 averaged with respect to the stationary measure, nu, and similarly for f bar 2, okay. So the idea basically is that for the limit problem, we don't have two processes anymore. We have just x, and the process y disappeared, and we have the stationary measure, okay? And we have the fixed point condition, so empty, the fluid empty is and the measure mu satisfy this condition, okay? And now, so the thing is here that what I would like to show is that I have an epsilon equilibria for this problem. So to do so, I first need to know that I have an equilibria for this one. But this is, for this one, in terms of only stopping time, I don't know, it might not exist, okay? So what we do is we go to randomized stopping. So how we define the randomized stopping? So for the effective problem and two-scale problems. So the set of strategies we defined through randomized stoppings, which are defined as regular kernel probabilities over omega times here is the Borelian sets over 0 capital T. And we also have this measurability assumption that for each time T and for any Borelian B, we have that KB is FTWX measurable, okay? So if you think about the standard stoppings, when you have a Dirac, it's of course satisfied. And then for the two-scale problem, the definition is exactly the same. The only difference is that here the measurability is required with respect to the big filtration. So, which is the definition of the two-scale epsilon mean-field game equilibria with randomized stopping? We say that K M mu is a two-scale epsilon mean-field game equilibria with randomized stopping if this holds for any admissible kernel. So it's what we have seen before, it's just that I replace the stopping time with the kernels. And we have this condition, okay? Where again I replace the indicator that T is smaller than tau with respect, I replace it with the kernels. So, we have the notion of effective mean-field game equilibria with randomized stopping, okay, which is this one is the same as before, and we have the averaged coefficients with respect to the stationary measure of the process Y. And what we prove that there exists we prove first that there exists an effective mean-field game equilibria with randomized stopping. So which are the ingredients? The first one is the existence of an effective mean-field game equilibria in the LP sense. So this is the first part of the talk, what I presented. And then we have a link between the LP mean-field game equilibria and the mean-field game equilibria with randomized stopping. So a one-to-one relation between the admissibility measures M from the linear programming approach and randomized stopping that I have introduced in the previous slide. So this is what we get. We prove that if this set of the admissibility measure, this can be written as measures associated to randomized stopping, okay? So using this, so the randomized stopping really allows us to go to the multi-scale structure. So we show that there exists a two-scale epsilon mean-field game equilibria for the problem, for the general problem. Okay, and which is the equilibria is basically you take the K star M star mu star from the limit problem, okay, the effective mean-field game equilibria, and then you define the measures for the two-scale problems where in this way, okay, and we can show that this is an epsilon mean-field game equilibria. So which are the ingredients of the proof? So there are the strong averaging results for the slow variable. We use the discretization procedure for the slow variable combined with Poisson equation techniques. So the main difficulty is that for us, the payoffs depend on the fast scale. And we also, the fact also that we have the common noise. So these two things put together create some technical difficulties. Then we use the projection of kernels with respect to the big filtration into admissible kernels with respect to the small filtration. And we use also, of course, the property, the equilibria property for the effective problem. Okay, for those who are curious, I can, of course, present also the elements of the proof between the link, the clear link between the set of admissible measures and randomized stopping, in case you are interested. I will do it only if someone is interested, because I think I have the time to do it. And what I would like to mention as a nice result when we prove the equivalence between the set of admissible measures, and this R1 is basically the set of measures associated to randomized stopping, and this is the closure of the convex hull of the set of measures associated with strict stopping. Okay, so we have an equality between also between the closure of the convex hull of the measure associated to strict stopping. So we see that indeed this set R is the minimal set which can be considered, which contains the measure associated with strict stopping, but which is also convex and compact. I would like also to mention joint work with other developments, joint work with Renyoan and Jody Dianetti and Giorgio Ferrari, where we develop a foundational theory for reinforcement learning for optimal stopping mean-field games. So in that case, as is usual in reinforcement learning, we add an entropy functional. So this will make the performance functional to be nonlinear with respect to the randomized stopping, because in that case we use the notion of equilibria in terms of randomized stopping, and we interpret the equilibria in terms of singular controls, but the singular controls that we denote by Xit are exactly our randomized kernels, okay? The ones that I have introduced before. And we also extend the fictitious play algorithm that I presented to the nonlinear setting, and we prove their convergence, and we do it in both settings where you have the Last-Lyons monotonicity condition, but also the supermodularity condition. So this paper where we do the theoretical study is available on arXiv, and now we are working on the algorithm, and I think this will be soon available as well. And here is a list of references in case you are interested, and I think I will stop here. Thank you very much for your attention.
For the very nice talk on the game of optimal stopping. Do we have questions from the audience?
For your slow-fast dynamics, did I catch correctly that the fast system dynamics somehow only enters through a distribution into the system?
You mean for the limit problem? Yes, it's through the stationary measure.
Right.
So okay, for the for the problem, the two-scale problem that I write, I have to process. I have both process, the slow and the fast.
Okay.
For the limit, I just have the measure, yes, for y.
Thank you.
I actually have a question. If we want to understand a mean field game of optimal stopping with only common noise, no idiosyncratic noise, then what would be a good framework to study that? Was this fast-slow?
Yes. So if you don't, what we do, so this will be, actually, if you don't have idiosyncratic noise, and if you assume, if you have only common noise, actually the analysis becomes even more simpler.
Okay.
Because the problem is actually the main difficulties come when you have the couple, you have idiosyncratic noise, the common noise, you have the payoff which depends on the fast process, and if you would not have the common noise, is also quite simple.
Okay.
And the combination of the two is the most difficult in terms of technical.
If no further questions, let's thank Roxana for the nice talk.